right, so
All right, this is
nice
more
to
like
meet you. Yeah. So it's about 6 o'clock now. Maybe we can start with the speaker here. Bill is the our chair for the local line member. So Bill, you want to start when you're ready?
sure. I'll just officially start this meeting as soon as I get all my clicks in a row here. All right. So here we are, the monthly meeting. This is a joint meeting between the Life Member Affinity Group in the Central Texas section and the Consultants Network Affinity Group in the Central Texas section, and some other R5 Life Member groups. We have Houston, Galveston Bay, Dallas, and Denver, I think, as our co-hosts represented here tonight.
And Houston.
Yeah. Yes, I mentioned Houston. I hope maybe it didn't come out.
Okay.
The Consultants Network is an organization to pull consultants together so we can help each other out. Life Member is a group you automatically become a member of when you're at least 65 years old, and that plus your years of IEEE membership, sum to greater than 100. The Life Member Group is a little bit broader in its interests. We like to have meetings, mostly technical, but sometimes general interest. And we are not averse to going on field trips to institutions around the area, which we have done from time to time. Here's a list of the officers for each group. You'll notice, I'm not going to dwell on this. You'll notice some overlap between the two groups. And I will alert you, we will spend more time on this next month, because next month we get into the IEEE election cycle, and IEEE is tightening the screws on how we conduct elections. So we are going to have to follow policy a little more than we have in the past. And that means we start in August with call for nominations. Next month's meeting is Imaging the Earth Using Satellites. Tom Babb of Sky-Fi. It'll be August 15th at 6 p.m. Another interesting talk. And then I want to mention that there is an extra meeting this month. We have been invited by the Fort Worth Life Member Affinity Group to co-host this Estate Planning 101, Protecting Your Family and Legacy. A link to the registration was included in the announcement of tonight's meeting to the Consultants Network distribution list. And all Life members in the section will receive at least one more e-notice about this meeting with a link going out Sunday. If neither of those covers you and you're interested in this meeting, send an email to Kai or me, and we will give you the registration link. It's a week from tonight, not exactly a week. It's a week from today at 12 noon, Thursday, July 25th, which brings us finally to tonight's meeting.
Bill, before
yes.
you get there, regarding that estate planning next week, you mentioned about the Central Texas Networking Consultants Network. So did we approve it, or do we have to approve it, or can we just check it and say, hey, let's join this meeting?
You can join. Anybody can join the meeting. It's open. So what I was trying to say is there is a link to the registration page for that meeting in the announcement for tonight's meeting that went out to the Consultants Network distribution list.
Okay, great. I don't know. Maybe I need to inform Wei Ping to put it on the website.
Yeah, that's your call. So
Okay.
just for everybody else's benefit, Louis is the chair of the Consultants Network here in Central Texas section. And yeah, that's your call.
Thank you.
All right. So finally, we get to Kendra Cook. Space Technology for Interplanetary Exploration is the title of her talk tonight. She's a senior systems engineer at JPL and currently lead spacecraft operations system engineer for NASA's flagship mission, Europa Clipper. And prior to joining JPL, she's done a number of things working for US government on a number of technology development programs, and then was an officer in the Air Force for 7 years as an aerospace engineer. She's accredited. She has a BS in aerospace engineering from Boston University and master's in astronautical engineering and computer engineering from Air Force Institute of Technology, and certified for various number of things that you can see in there, but we want to get on to tonight's talk. So we will turn it over to Kendra as soon as I figure out how to stop sharing. Okay.
Thanks, Bill. All right, let me share my screen. All right, can you guys all hear me okay?
Yes.
All right, I will leave my video on for a few minutes, but I've got a bunch of videos and stuff in my slides. And so to preserve bandwidth, I may end up having to turn my video off, but I'll leave it on just to start with, and then you guys just holler if I start breaking up.
I just want to add one thing to all the listeners. Please turn off the video so that we can save some bandwidth for Kendra.
Oh, thanks. Thank you. All right, so a special thanks to Kai Wong for inviting me tonight. I met Kai when I was in Texas at the IEEE Life Members conference back in April, and he invited me to come and give this talk to you guys tonight. So thanks for the invitation. I'm really happy to be here. All right. So thanks to Bill for the kind introduction. I won't belabor this, but I do want to just point out the picture on the right-hand side. That's me commanding the Europa Clipper spacecraft inside our thermal vacuum chamber at JPL a couple months ago. That's going to come into play later in the talk, so I wanted to make sure to point that one out so that you can see that I really do get to play with satellites in my day job. All right, so I want to talk to you guys about the space technology that is required to do interplanetary exploration. And the way I'm going to do this is through two case studies. The first one is an existing program that is in operations on Mars. It's the Mars Perseverance Rover. You guys have probably heard of it as Mars 2020 or Perseverance. And then I want to also talk about Europa Clipper, which is the mission that I work on. And that one is a future mission. It's coming up. We're going to launch in October. So I want to do a little bit of comparing and contrasting and talking about the technology that we're working with, not only because it's really cool and it's very exciting, but also because it was born a lot of times out of necessity. So hopefully this will be informative to you guys. I'm not sure if you guys have space backgrounds or not, so feel free to holler if you guys have any questions. And I'll also leave time at the end to take questions. All right, so the Mars 2020 Perseverance Rover landed on Mars autonomously back in 2020, as the name implies. And one of the key challenges that we had to deal with, oh, that's not me again. Let's see if I can turn that off. One of the key challenges that we had to deal with is the time delay and the communication delay. So if we want to say hello to the rover, it takes 7 minutes. If we want to hear it say hello back, that takes another 7 minutes. So 14 minutes round trip. This means that anything that we want to do with the Perseverance Rover, it cannot be done in real time. You cannot joystick it. You can't just drive it around like I used to make fun of my husband because he actually worked on the Mars 2020 rover. And I would always say that I was his backseat driver, but really I wasn't, because they had to do a lot of planning in advance. So they weren't actually driving it on the surface in real time. And so when you think about autonomous vehicles on Earth, think about where we're at with that. They have sensors, they're getting pretty good, but they're nowhere close to what you have to do to be able to land and operate a vehicle on another planet. So what this is doing is it actually drives to a rock that we tell it to. We say, go to this one over here. It has to pick the path. It has to go around obstacles or go through sand or go over different things. It has to get to the rock, drill a sample, collect it, put it in its belly, and cache it for later. We're going to go back and get it with the Mars sample return. And it has to do that all without any humans in the loop. And so that is pretty amazing. All the algorithms and all the sequences that have to get built and tested. And I'm going to talk in a few slides about how we do that. But this is all done completely autonomously. This is just a little video of it actually putting those samples up into its belly. Skip ahead. All right, let's see. So landing and operating on Mars isn't new to JPL. We've actually landed 5 of the last 6 rovers. China did get one on there in 2021, and so they have a rover on Mars now as well. This is a little bit of a dated graphic, but it just kind of shows you the context of we've got a bunch of rovers on the ground. We actually have a bunch of satellites in orbit around Mars that help us with that communication, partly because of orbital dynamics and where the planets are in relationship to each other. It helps us to have another satellite that's orbiting Mars to be able to collect our request, beam it down to the rover does its thing, it sends the data back up to that satellite, and it shoots it back to JPL. And so one of the cool things about JPL, I don't know if you guys have ever had a chance to visit, but we have a mission operations center there, and there's a big seal on the bottom that says Center of the Universe. And it's one of my favorite places, but it's because any interplanetary communications comes through that site, and then it gets redistributed out to the scientists and other organizations. So any satellites that are operating in deep space come through JPL first. So one of the questions that we're trying to answer is, are we alone? And that's up for debate depending on which camp you're in. But one of the things we're trying to do with the Mars 2020 rover is send it to the most likely place that we would be able to find these microbiome, microscopic signs of life. So this is a picture of Jezero Crater. This is where we landed. And this used to be an old lake delta, they think. And so the scientists at NASA believe that this is the most likely place that we would find signs of past life on Mars. The other thing that you'll notice, being engineers, is that this is a very big, flat, empty place. And yes, that is true. That is another reason why we picked this location. Because, like I said, everything that the Mars 2020 rover does, it has to do it autonomously. And so we didn't want it crashing into a mountain, getting stuck on a boulder, falling into a crevasse, so we picked this really flat, big, open space to give it the highest likelihood of success on its landing as possible. Because by the time we hear back, it will have been alive or dead on the surface for 7 minutes. So it has to do all of that on its own and get to where it needs to go by itself. It actually even picked its own landing spot. So it had some radars that were pointed down, and it did its own calculations to find the most likely place for success for it to land within certain parameters. Okay, so how do we do all this? One of the things that I mentioned earlier was we have to write all these algorithms, we have to write sequences, we have to build hardware for all of this stuff to happen autonomously because of the communication delay. So this is what we call an engineering model. And it is basically an identical replica of the Mars 2020 rover that's operating in space. But we have it here on Earth at JPL. And it lives in this big garage. It's not sexy or anything, but they can roll it right out into what we call a Mars yard. And this is a big place at JPL where it has sand and dirt and rocks and boulders of all the different kinds that we are seeing on Mars, or that we think we're going to encounter on Mars. And that way, whatever we want the real one to do, we can do it on this one first. And so we do things like, if we have to do a flight software upload, or we have to patch something in flight software, we'll send it to this one first and make sure it doesn't break anything before we send it to the real one. We can also test out equipment. For example, we had an instrument that got damaged during some severe weather on Mars. They had a really bad windstorm, and it broke one of our instruments. And so we replicated that with this one to see how could we operate that instrument in a suboptimal manner, but still get useful science data from it. And so we were able to manipulate this one to basically mimic what we were seeing there. Another interesting thing that we did with this one is that the real Mars Perseverance Rover got stuck in some sand. And so we basically drove this one out, buried it in some sand, how we expected the other one to be, and figured out how to get it out of there, which, spoiler, is we had to drive it out backwards. So we drove it backwards up out of the sand on Earth and proved that that was going to work. And then we sent the same commands to the one on Mars and got it unstuck. So it was a pretty useful tool to have on Earth when you can't just call AAA and have them come and tow you out on Mars. As a side note, not related to this one, but Spirit, if you guys remember the twin rovers, Spirit and Opportunity, that launched in the mid 2000s, Spirit actually broke one of its legs. So one of these front joints got broken, and it couldn't drive forward because that wheel was basically disabled. And so what they ended up doing was figuring out that they could drive it backwards and drag that leg behind it. And so they did for 3.5 years. And they continued to get more science data with a broken rover. And the craziest part to me is that this really ended up being an opportunity in disguise, because we basically scraped the surface of Mars off with this leg that we were dragging behind. And that was never the plan. We didn't expect anything from it. But because they were able to unearth the top couple inches along a wide swath of where it was going, we were able to do really great science with that data. And so I just think it's really cool that we are able to take things like damaged equipment or things that are on their last leg, literally, and come up with great ways to use them to get even more science data out of them. All right, so some of you guys probably have heard of Ingenuity, and this is the actual Ingenuity helicopter that was the tech demo that went up with the Mars Perseverance Rover. And what's crazy is that this was supposed to only fly between like 1 and 5 flights in the first 30 days. It was just a proof of concept to show that we could fly a helicopter on another planet. And the reason why that's such a big deal is because Mars only has 10% of the atmosphere that Earth has. And so for it to fly on Mars is effectively us flying a helicopter at 22 miles above the Earth. Have you guys ever heard of a helicopter flying that high? No, because it's really, really hard. There is like no atmosphere up there. The highest helicopter on record on Earth has only flown up to 40,000 feet, which is like 7.5 miles. And most of the time they fly around 10,000 feet, which is like less than 2 miles off the surface. So for us to fly it at 22 miles off the surface equivalently was huge. And just to help explain this, on Earth, the rotors on a helicopter spin roughly 500 to 600 RPMs, and this little guy had to spin at 2,400 to 2,700 RPMs to get the same kind of lift. So huge, huge, huge engineering accomplishment. They actually had a really hard time testing this on the ground because of the drag of the Earth's atmosphere.
Yeah, you want to watch this?
Running. I think you have an open mic. There we go. So they were actually having a hard time testing this on the Earth because it kept melting. It would get so hot because of the friction of our atmosphere. So we ended up having to put it in a thermal vacuum chamber, suck all the air out, and then test it there to be able to prove that it would be able to fly. The other really cool thing about this and why we're trying to fly on another planet is if we were to send humans to Mars, we don't want to have to drive rovers around because they're really slow. And so this was the proof of concept that we could theoretically fly from, base over here to a base over there. So it just was a smashing success, and I'm really, really proud of what we did with this little helicopter. So here's an actual video that the rover took of the helicopter flying. So I'm gonna let you guys see it because it's just really cool to see this in action. So that is live footage from Mars. Doesn't go very far, it doesn't go very fast, but it's pretty cool. I think it touches down here. Oh, so I mentioned it was only supposed to fly 1 to 5 missions over 30 days. It actually ended up flying 72 missions over 3 years. So it did finally die. It had a hard landing. One of the blades broke off of one of the rotors, so it finally did die. But it went way farther than anybody was expecting it to, which was pretty cool. All right, let's see here. So then here is the first ever selfie on Mars. This was taken by the Watson camera, and you can see the Mars rover is looking at you, and then he looks back to see Ingenuity there in the background along with the treads. So this is actually a series of 37 images that were stitched together to make this little graphic. But it is officially the first ever selfie on another planet. And okay, I have to tell you guys my favorite story. It is not necessarily about the technology, but it is about engineers, and it makes me laugh. So you guys see the treads here, and they're pretty benign. One of the earlier rovers, we had wanted to put JPL into the treads, and big NASA was like, you guys cannot go around driving on another planet and writing your name all over in the sand. And so they said, no, you cannot put JPL in the treads. So the engineers came up with this reason why they had to make all these like big circles and little circles and different things in the treads. And they came up with this very logical, rational reason of why it had to be this way. And it passed muster, and off it went, and it landed on Mars, and it started driving around. And somebody took a look at the treads and got to looking at it, and they were like, you guys. And we were spelling JPL, JPL, JPL in Morse code all over Mars. And so it just made me laugh because we did not like the answer that they said, no, we couldn't do that. So somebody got really smart and figured out how to do it in Morse code. So alas, since they got busted with that one, we had to go back to putting normal treads on this one. So sad story for this one. All right, another thing that we have to think about when we're operating in international or interstellar space is the weather. So back when I put these slides together, it was in February. The high was -4 and the low was -108. Now, I live in Montana and it gets really cold here. I think this year it got down to -65. That's pretty cold. And so not only does this technology have to operate in those ridiculously cold temperatures, they have to actually thrive in them. They have to be able to do their job and do them better than we ever expected. And so what we do is we put them in thermal vacuum chambers, and that was what I was doing on that first page where I was sitting there commanding the Europa Clipper spacecraft, is we put them in these big chambers, we pump them down, we get all that oxygen out of there, and then we can make them really, really hot and really, really cold. And we turn on instruments and we do different mechanism motions, and we do all these things to make sure that when they get out into space that they can deal with these really harsh environments that they're going to see that we don't necessarily see on Earth. All right, one of the coolest instruments in my mind for Mars 2020 is the MOXIE instrument. And that basically extracts oxygen from the carbon dioxide in the atmosphere on Mars, which remember is only 10% of Earth's atmosphere, and it turns it into usable liquid oxygen. So if any of you guys have seen The Martian, that's what they used to lift off when he was getting boosted back up off of Mars, is they had liquid oxygen that they had made from their own cells. Well, this is not science fiction, this is real life, and we actually did it. And so this was a great first step in demonstrating that we can take oxygen out of the minimal atmosphere that they have on Mars and turn it into liquid oxygen for fuel, or make it into breathable oxygen for astronauts. And speaking of astronauts, they want to go to Mars. There's these people, they want to go to Mars. And when we sent the Mars Perseverance Rover, it took 7 months. Now, that was on a good day. If it's on a bad day, it takes about 2 years to get there. And just imagine being in a 500 square foot spacecraft with you and your 3 closest buddies for 7 months or 2 years. You're going to get tired of people's jokes pretty fast. That is a very long time. And so NASA is actually studying the impacts on humans. There's on the psychology, on the physiology of being sequestered in these little tiny spacecrafts for that long. And so as a side detour, I wanted to show a slide on the NASA Hera project. So this is the Human Exploration Research Analog project that NASA does. And this is me up in the top picture. This is a better picture of what the whole thing looks like on the bottom. I'm actually I'm in the candidate pool for one of the final missions this year, where you basically go into this little spaceship, and they only do it for 45 days because they figure that they can see the cycle of both physiological and psychological impacts of being in this little tiny space in a 45-day period. So they don't make you do it for 7 months, thankfully. But you go in there with 4 people for 45 days. It's 650 square feet. There's no privacy. You are together all the time. they actually induce stress. So they make you stay awake for 36 hours. They give you procedures that are not well written or complete or even correct. And you have to do experiments, and you have to figure out how to do all this with sleep deprivation and the anxiety of being watched all the time, because you're basically like the rat with the cheese, and they have all the cameras that are watching you, and they monitor your pupils and your heart rate and all this stuff. And so some people are like, does that sound like fun? And I don't know that I would call it fun, but I think it's a really interesting experiment, and I think it's really valuable for science, because if we are actually going to go to space, this is a huge aspect of it. And so they only pick people that are qualified to be astronaut candidates. So you have to meet all the criteria, all the physical stuff, all the qualifications, and they call you an analog astronaut. So the only difference is you don't actually go to space, you just go to space in this little tiny spaceship. So we'll see what happens there. Maybe next year I'll come back and talk to you guys about my experience living in a little tiny spaceship for 45 days. All right, so one more gratuitous video of the rover driving. It does not actually go this fast. This is sped up a lot. It is very, very slow, but you cannot get too many videos of the Mars rover driving around. I think it's just really cool. All right, and then the last slide that I have on the Mars 2020 side of the house is this one. And so we had a supersonic parachute on the Mars Perseverance Rover that helped it land. And so we had a heat shield as it came into the entry, descent, and landing, and that slowed it down to about 1,000 miles an hour. And then this supersonic parachute took over, and it is the biggest parachute ever. It's 180 pounds, it's 70 feet across, and it had to slow it down from 1,000 miles an hour to 200 miles an hour when we then had thrusters that we came down on, and the thrusters could take over. So this is an actual series of images as it deployed on a test run before we launched. But then up on the left-hand corner, this is an actual picture of the real parachute when it was landing. So it took a selfie with the camera on board. So what I like is JPL also hides little Easter eggs and things, and our motto is to dare mighty things, and you'll see that here. They wrote it in the parachute itself. All right, so I want to switch gears, and I want to talk about Europa Clipper for two reasons. One is that I work on it and I'm really excited about it, and two is that, you know, JPL and NASA and the world have put a lot of money and resources into going to Mars. And what's interesting to me is that going to Mars gives you, in my opinion, do not quote me on this, I feel like it gives you limited value, because all you're looking for is signs of past life, right? It has great conditions, it might be there. We'll find out hopefully with our Mars sample return project when we bring those cached samples back. But the great thing about Europa is that we think it actually has a really high potential for current life. So it has a predicted warm ocean under this thick ice crust, and we think that there's active geology, and I'm going to show you some of the stuff that makes us think that. And so we think that it has all the right things that it needs to have actual life on Europa. So we think that it has a similar makeup of Earth, where it has a metallic core surrounded by rock and this ocean surrounded by an ice crust. The interesting thing is Europa is maybe like the quarter of the size of Earth, but we think that it has twice as much water as all of Earth underneath the ice. And so if that's true, that is a huge amount of water. Now, some of you guys might be thinking, that's pretty far away. It's 5 times, if you think about an AU distance is the distance between the sun and Earth, it's 5 of those to get out to Europa. So it is really far away. How is there any liquid water on that planet or on that moon because it's so cold? Well, turns out Europa has more than just the solar heat, which is what we have. It also has something called tidal flexing, which causes tidal heating. And so on the left, you'll see the little graphic of Europa orbiting Jupiter. And Jupiter is directly, which means the orbit is a little bit off-centered. And as it gets closer, the gravitational pull of Jupiter actually literally like stretches out Europa, and then when it gets up to the top, it shrinks it back down again because that gravitational pull isn't as strong. And the scientists think that this kind of motion, this tidal heating, is enough to cause friction that keeps that water warm. And so that's what's keeping it from not just all being a frozen ice crust. The other thing is that we think there's convection. We think that there's warm hydrothermal vents under the ocean that are causing warm air to come up, which also heat the subsurface of the ice. I'll show you, I've got another picture that's kind of zoomed in on the spot. It's like a subsurface lake that we think is caused by some of these geothermal vents underneath the water. So these are what we call chaos regions. You can see it just a tiny bit in this picture. I'm going to show you a few of these. We don't know exactly what causes that, but one of the theories is that we have these hydrothermal vents under the water that come up and it warms the water. It melts some of this ice, and then you basically get what are like icebergs that are floating around and hitting each other and disrupting the surface. And so that's one of the things we're going to go look at with Europa Clipper, is to try to figure out like what's actually going on here and why do we see all these weird striations and different topological features on Europa. So like I mentioned, we've got a lot more water than on Earth's oceans. We think that that has essential elements necessary for life. So oxygen, nitrogen, hydrogen, all those good things. We think that there's chemical energy from above and below. The above part is more radiation, so I'm not sure that we would want to eat anything that we find out there, but we think that there's energy sources that could be a potential for life. And we think that there's a lot of stability there because it's been there for a long, long time. So one of the things I want to show you on the next slide, it's a video with words. So I'm going to not talk for like 30 seconds while I show you this video. A lot of people wonder, like, why do we care so much about these hydrothermal vents? So what I'm going to show you on the next slide is a video of Earth. So don't get too excited. It is not Europa. It is a video of what we see on Earth, but it'll give you an idea of what we are expecting or would love to see if it worked out like this on Europa. So watch this little video real quick.
So right now we are at a depth of 3,275 meters, looking at an incredible black smoker hydrothermal vent chimney. That black fluid coming out there is likely between 300 and 400 degrees centigrade. These ecosystems are literally islands or oases amongst what is cliche, and the deep sea is definitely not a desert, but relatively islands of abundant fauna, islands of life in what is a usually desert-like deep sea flow. Oh, this is so cool! What, 27 meters high? 30 meters high.
All right, so that's just a little snippet of why we get so excited when we talk about the potential for hydrothermal vents on Europa, because you never know what little creatures are living down there based on the heat and the chemicals that are coming out of there. All right, so that's the context of Europa. I haven't even talked to you about any of the cool space technology that we're going to implement to get there or what we're going to do when we're there. So that's what I want to talk about now. But that kind of gives you the idea of why we get so excited when we talk about Europa. All right, so the Europa Clipper mission is the next big NASA flagship mission that is going out to Europa. And the goal is to explore Europa and investigate the habitability. So we're gonna go, we've had a couple spacecraft take pictures of it, had the Hubble telescope pictures, we had Voyager take some pictures as it flew by, but we wanna really go study it. And what's really cool is that we have in-situ and remote sensing instruments that I'm going to talk to you guys about. But first, a quick overview of the Europa Clipper mission. So we launch right here, October 10th of 2024. That is less than 3 months away. It is definitely go time in Europa land at JPL. we're flying on what's called a mega trajectory, a Mars-Earth gravity assist. And so what we're doing is we fly, let's see if you guys can see my cursor. We fly by Mars. We use this gravitational pull to basically slingshot us back around. We hit Earth again in December of 2026, and we use Earth's gravity to then slingshot us all the way out to Jupiter, and we get to Jupiter in 2030. So what's really interesting is I helped perform the trade study of what are we going to do about the spacecraft in this little time frame, because as you notice, it is actually closer to the Earth or closer to the sun than the Earth is, and it gets really, really hot. But our spacecraft is made to operate at 5 AU, where it's really, really cold. And so how do you fly your spacecraft for several months in this extreme heat environment without having to put a bunch of unnecessary blankets and shielding and all this stuff on it, because it only matters for this short amount of time, and then forevermore it's going to be really cold. And so what we ended up doing is we're using our high gain antenna as basically a shield, and we're going to keep all of our sensitive electronics behind it. So as we go by the sun, we're going to do like this kind of a motion, and that heat shield, the antenna is going to take all of that heat. If something happens and we were to like turn the spacecraft, everything would get fried and it would be mission over. So it's really, really important that we have a really good guidance and navigation and control system in our spacecraft to make sure that we can like protect all of our sensitive instruments during this narrow window where it's going to be super hot. All right, so this is a picture, a graphic, an illustration of Europa's orbit. Now we're actually in orbit around Jupiter, not around Europa. And we do this because Jupiter has a really strong radiation environment, as you can see down here in the bottom right-hand picture. And if we were to just orbit Europa, we would effectively be in that high radiation environment all the time. And so what we need to do is we need to get out of that environment so that we can allow our computers to reset and our instruments to have a break, and our solar panels even are going to be degraded by this really intense radiation environment. The other cool thing that you can see with this animation is that the way that we are flying our orbits, you can't see it in this one, but we fly around Ganymede and Io also to help reshape the orbit. And so what happens is when we go to fly by Europa, we can actually image about 90% of them. And so it's just kind of a cool graphic of showing different slices that we're going to get based on how we're going to fly by it. All right, so the Europa Clipper spacecraft is a behemoth. It is about, how long? It's like, hang on, where's my notes at? Oh yeah, 100 meters tip to tip. So that's like the length of a basketball court. So it's really big. It's about 6 meters high, so 20 feet high or so, and it weighs 6,000 kilograms. And so this is a huge, huge, huge satellite. We are actually going to do 45 flybys of Europa, and they range anywhere from 1,700 miles off the surface to 16 miles off the surface. So we're getting within 25 kilometers of the surface of Europa with this giant satellite. It's going to be very sporty, but when I say sporty, I don't mean like sports car sporty. It's like a giant bus that we have to maneuver and make sure that we can do what we need to do. Like I said, we have in situ and remote sensing instruments. And I'm going to show you some gratuitous pictures on the next page. But we've got 10 different instruments that do all different kinds of things. So for example, these are our remote sensing ones. And we have like the EIS, NAC and WAC. We have a narrow angle camera and a wide angle camera that produces high resolution images of the surface. We've got the Reason antenna. This is the ice penetrating radar. So this is more like when you think about autonomous vehicles and how they have radar that goes down subsurface to the ground and maps the features down there, and that's how they know where they're at. That's what this is basically doing. And so it's going to map the thickness of the ice. It's going to find us the shallowest part of the ice so that if we were to go and send a lander back there, we can land it on the thinnest part of the ice instead of the thickest part, because then we would have the highest likelihood of actually drilling through it. We've got ETHEMIS, which is the thermal instrument. that's going to survey the frozen surface and look for temperature variations that could indicate warm plumes that are coming up. Some of the in-situ instruments are actually the coolest ones in my mind. ECM is a magnetometer. I'm going to show you a whole slide just on this one, so stand by on that. But SUDA and mass specs, these are really cool to me because when we get down to like that 45 kilometers off the surface, these are basically like open mouths, and we're going to fly through the atmosphere and we're going to ingest all the particles that we get, and we're going to do analysis on them to see what it is that's actually made of. So we can tell, are there bits of dirt flying up? Are there molecules of water? Is it just, you know, any organic particulates, anything like that? So these actually physically take the atmosphere and ingest it into the spacecraft, which is pretty cool. All right, so this is the slide I wanted to talk to you guys about ECM. So Europa has its own magnetic field, which you can see right here, but it is also within Jupiter's magnetic field. And so it's a really tricky environment to work in because we want to just be looking at Europa, but we have to back out all of the magnetic field from Jupiter. Well, the other thing that's really interesting that makes it very difficult is Europa Clipper also has a magnetic field, has a huge magnetic field. We have over 300 individual sources of magnetics on our spacecraft. So we had to model it so that we could back all of those out from the data and be able to understand when we see something that it's actually coming from Europa and not self-inflicted. And so one of the things that you'll see, I think you can see it in this graphic when it pops the spacecraft back up on here, is that we have what's called a magnetic boom. Oh yeah, here you go. And so ECM is all the way out here on the end of the boom. It's 8.5 meters away from the spacecraft, because we're trying to get it as far away from the self-inflicted magnetic fields as possible to help us be able to say, okay, yes, what we're seeing is actually coming from Europa. All right, and then this is just a graphic or a artist rendition of what it would look like if we actually could fly through a plume. And so that's the goal, right? Like we don't think they're there all the time, but we don't really know. And so if we can find one that's an opportunity, like this could be what you can envision our spacecraft doing, is like flying through it, actually collecting the particles of the plume itself to see what's going on. Where did it come from? What does it contain? And all that. All right, and then this is my last slide. So I will let this play. I'll take questions. And before I do though, this is a series of images that are real images of varying quality that you'll see. It all kind of superimpose now and we'll get closer and closer and closer. But these are all pictures from other missions that we used to create this video of what it would look like if we're zooming in on one of these chaos regions. And with that, I will take questions.
Louis, can you read out loud the question so that everybody can understand? Louis?
Okay, let's see. I think most of the questions are just posted a few minutes ago. I'll start with this one. How does Europa's thick ice crust impact the possible life forms that might be present, and why is there so much of water frozen or liquid?
So that's a really interesting question. I am an engineer by trade and not a scientist, so I cannot give you like the scientific answer, but I'll give you my answer, which is I think it could impact it positively and negatively. I think on the positive side, it's probably doing a lot to shield whatever life there might be in that liquid ocean from Jupiter's radiation. But I also think that maybe it would inhibit them from having any exposure to the atmosphere. So whatever is down there has to strictly live off of what's in the water and what's coming out of these hydrothermal vents. So it almost sequesters it into its own isolated containment region, if you will. But I don't know if that's a good thing or a bad thing.
Okay.
Was there a second part of that question about the ice?
Well, I mean, obviously, it's so cold out there. It's quite reasonable to have a thick ice crust over the whole moon or planet. Moon, I guess, not.
Yeah, they think it's between 5. Yeah, they think it's between 5 and 15 kilometers thick. So it's pretty thick.
It is pretty thick then. Okay. All right, another question. It sounds like Europa is a bit of an atmosphere since you plan to scoop up some. How dense is the atmosphere?
I don't think we know yet. I think that's one of the things that we're going to try to find out with Europa Clipper. So far, we've really only gotten like images, but we don't have any kind of spectroscopy or anything like that yet. And so that's one of the things we're going to look for when we get out there.
Okay, this is another one. Is there a short list of the biggest engineering challenges for any and all of the probes that you've been involved with?
I think I mentioned a lot of them. If I had to make my short list based on the things we talked about today, it's communication delay, a harsh environment, having to do all autonomous operations. I think those are kind of the biggest ones in my mind that are common amongst anywhere you want to go. And then there's other things with like heat or cold, and that comes into the environmental conversation, but that is more depending on, are you going to like which planet and that kind of thing. But I'd say communication delays and in the harsh environment are like the short list in my mind.
Okay. And here's one. What engineering marvels are currently being tested toward drilling remotely through this thick, tough ice?
So that's a great question. I don't know that we're actually doing work on that yet. So I know that there was some pre-phase A studies done on the Europa Lander mission several years ago, back in like maybe the 2018, 2019 timeframe. And then they got squashed at that point. But people have talked about it. My sister is actually a petroleum and geological engineer, and she does drilling in the oil and gas industry. And I've talked to her about coming to JPL and pitching that we should get oil and gas people to partner with us because they know how to do drilling, but it would be a whole nother level of complexity doing it on another planet, you know? But I don't think we've gotten that far yet. So I think we've thought about it, but no, I wouldn't call them engineering marvels at this point yet.
All right. How many chaos regions does Europa have? Can they be seen with terrestrial telescopes?
Ooh, good question. I don't know, and I don't know. Those are great questions, though. I don't know if there's specific numbered regions. I know this one has a name, but you probably Google it. And if you have a really good telescope and you can get a picture of it, send it to me because that would be amazing. So I don't know if you can actually see that, though, from here.
Here's an easy one. Why pick Europa? Or maybe difficult?
So that is the easy one in my mind because it's the place where we think there's the highest likelihood for present life. There's no other planet that's easily accessible in our lifetime within our technological capabilities right now to get to. So this is like the number one place. If we're going to find life in our solar system, like this is where it's going to be. So to me, that's the easy question of why we should go there.
I like to kind of add one to your comment. It's great, to pick Europa, but as we know, it's in a moon of Jupiter, and you have to navigate through that asteroid belt. Is that a very challenging prospect?
I don't think so. We have really good navigation team at JPL, and I think that that's all modeled pretty well. And so I don't think that that is a real concern. I mean, it's something we have to take into account, but I don't think that that's something that's an obstacle in my mind.
Oh, okay. I think maybe in my mind or some people's mind, this asteroid belt is like a giant screen of rocks, but then they might be actually miles and miles apart, right? So it's not like they feet or meters apart.
Right. It's not like in the movies, I don't think. So.
Okay, not like in Star Wars.
Right. Yes.
Okay, this looks like a pretty technical question here. Can you discuss the possibility of a delay in launching Europa Clipper due to the Infineon MOSFET radiation sensitivity issue.
Yes, I figured I would get a question like that today. For those of you guys who haven't heard, this came out in the news earlier this week, I think. We're having a MOSFET issue. And basically what that means is I talked a little bit about Jupiter's radiation environment, and the MOSFETs, which are a component on the spacecraft, we have like 1,000 of them. They are supposed to be radiation tolerant, and they aren't for various reasons. They are not tolerant enough for the environment that we're going to operate in, which means we would do one flyby and we would die. And that's not acceptable. And so there's a Tiger team right now that's looking into what are the potential mitigations that we can do. You know, maybe we change our orbits, maybe we do one flyby and then we have like a whole bunch of months to recover from it, and then we do another one. There's people way smarter than I am that are looking into what we can do about that. And it came out this week that there might be a launch delay because of that. I think it's still too early to tell. We should know more in August what's going to happen. But there are other launch opportunities for Clipper after this window. And so we'll just have to see if they can come up with a mitigation strategy in the next couple months, or if they're going to need more time to figure that one out.
Okay, someone just commented on that question. Only P-channel MOSFETs are affected. Okay.
It's whatever ones we're using are the ones that are affected. So.
All right. Here's one more. Will you have a twin Clipper hanging out at JPL for the same reasons that you have a twin of the Mars rover?
We will, but not exactly, because it's so big. So we will have a system test bed, STB. We actually have 2 of them, and that has engineering models of the instruments themselves, and it has all the flight software, and we even have some other components like I think our telecom components are on there. So it's going to be a hybrid model of just like a computer simulation and different pieces of hardware. So it's not a full up, like we don't need the solar arrays and all that kind of stuff. We won't have that, but we'll have some of the key parts, and we will use that for any time we go to uplink any of the sequences that we need. So we're going to do like 6-week-long sequences in cruise, for example, when we're going out there. We'll run those through the background of this STB and make sure that nothing bad happens. We send it to the spacecraft. So we will have something similar.
Great. I believe that's all the questions I've seen so far.
So I'll let,
People, you guys can actually turn on the audio now and ask questions live if you like to.
yeah, I'd like to add one. What microprocessor do you use in the control board or control system?
Say that again?
What microprocessor, CPU or NPU do you use for control?
I don't know off the top of my head.
Okay.
I'll have to get back to you on that guy. Other questions? I saw Bill's comment. I just pulled up my chat since I'm not sharing anymore. Space missions are hard. They are hard. You will notice that by the Falcon 9 failure that they had last week. That's going to be a big detriment to our program, even though we're using the Falcon 9 Heavy, or the Falcon Heavy, sorry, the Falcon Heavy for our mission. Any kind of failure with launch vehicles has the potential to also impact future missions, depending on what they find with those, if it was an engine problem or something like that. So it is hard. There's still failures even when you've got a lot of smart people working on it.
I'm sorry, I just muted myself. How about things like solar flares and things like that? Would they affect the mission too?
They do, and we have different ways that we can handle that. Well, as we get farther out, it becomes less of an issue, obviously, but we have ways that we can scrub our processors with our FPGAs and things like that. So it's not too bad. We just have to get out of town quicker than staying around, you know.
Yes, I'm sure all those electronics are mil spec, red hardened, and everything else, right?
Yep. Other questions?
Yes, any questions? Other questions?
I hear somebody Googling something. They're probably fact checking me right now.
Oh, let's see.
Then maybe-
Bill has a big comment here.
Let's see. Nice. Yeah, the comment on ingenuity. It was so cool. It was so neat to watch it and to see it be such a big success. It really surpassed all of our expectations for sure.
I guess some of that are public information, right? From JPL Lab. So
Mhm.
can you send us a link, all the link that you shown, and also a copy of your presentation?
Yes, I can. Yeah, I can send you a copy of my presentation. I think in the notes section, there's a bunch of links to different places that I grabbed things. A lot of it was generated by JPL, but it was approved for public release. So I'm happy to share it if you want to share it with your members. I'll just send it to you, Kai, and then you can distribute it as you want.
Thank you. We'll post it on our website.
Okay.
So we
Sounds
have
good.
38 people attending, 35 people attending. So pretty good
Yeah,
size.
can I ask one question?
Yeah.
Okay, so it's regarding the machine on the Mars. How do you communicate? Do you control it remotely, or is it based on the voice commands, or how do you basically operate and control its motion?
Which machine?
The spacecraft that you launch on the Mars, it travels and it finds the rocks or any material, and then it extracts the samples and all that you mentioned, right?
Yeah. Yeah, so you're talking about the rover or the one that's actually going to take off from Mars to launch to bring
Rover, I would say.
rover?
Yeah, rover. Yeah.
So what they do is they actually write sequences, code that says, go this far forward, look for this thing, do that. I don't know all the specifics of what exactly goes into their sequences because I'm not on the Mars 2020 mission, but it's all done by computer code. And so then they send up the binaries like zeros and ones, and the rover takes that in and deciphers what it is that they want it to do. So there's no like voice commands or anything like that because of the time delay. By the time we see anything, it would have happened 7 minutes ago. And so it has to all be thought of in advance. And then the rover, the cool thing about the rover is it has to be smart enough to know whether it gets it or not. And if it doesn't, then it just stops and it says, I don't know what to do. Either I'm stuck or I didn't understand or tell me again. And so it's interesting in that perspective where it can actually either do it or it just says, I can't do it. And here's why. And then you have to try again. But it's all done through computer code.
Okay, thank you.
Mhm.
Yeah, that answers my question. Thank you.
Yep.
Was Ingenuity autonomous on its flights, or how was it controlled?
Yep, it was autonomous also. So they would send it a sequence that says, take off, fly, 3 meters to the west, go up 5 meters, come down, go left, go right, and then land. And it had to do that all on its own.
Okay, Rahim has another little question here. What other projects were you involved in?
Yeah, that's a good question. So I started off my career in the Air Force and did a bunch of different technology demonstrators for them, mostly in support of Operation Iraqi Freedom and Operation Enduring Freedom. So it was all on the warfighter side. But then when I left there, I went and worked for the National Geospatial Intelligence Agency and did some work for them. And then one of my most favorite jobs that I can actually talk about is I worked for NOAA on the Cosmic 2 weather satellite program. And so I actually got to live in Taiwan, and I was the US government's liaison to the Taiwanese government on this joint weather satellite program. And so in the early days, we were like just developing our level 1 requirements and negotiating what we were going to try to do with the mission. We had to go out and actually get funding for it. We had to get ourselves a rocket. We had to get ourselves a ground site or ground stations to ingest the data. And then I ended up coming back to the US, but then I would commute back and forth to Taiwan for another 4 years. And I was the lead systems engineer on that program. So that launched in like the 2016 timeframe. And then I went to JPL and did some classified programs for them. And then I worked on mostly internal JPL stuff. They have a team called the A team and Team X, which is like a business proposal development team. And then I went to Clipper in like 2018. I did cybersecurity on Clipper for a while. I was the cruise phase lead, and then now I'm on the ops team. So I've been on Clipper pretty much for the last 6 years that I've been at JPL. So not too many NASA missions, but lots of different kinds of missions. That's pretty much what I can tell you.
When did Clipper start the program?
Oh man, Clipper started a long time ago. I want to say it was in proposals like 20 years ago. It was part of the decadal survey. I think the people I know that have been on it the longest have been on it for like 11 years, maybe 12 years. And that was kind of like the phase A of like when it really got started. So I'd say a solid decade, more than that. And one of the things I didn't mention is it's going to take us 5.5 years to get out to Europa. And so by the time you do that, I mean, somebody could spend a whole career working on it because we're going to operate it out there for about 5 years. So if they started on it at phase A, they could theoretically work on it for 20 years and get a whole career out of it, which would be crazy.
Was that helicopter tethered, or did it use battery power?
Nope, it had a battery on it. Yeah, there was no tether. You can fact check me on that. I'm like 99% sure that's true.
So if someone wants to get into this field, what type of qualifications are required? I suppose at least a master's, probably a PhD would be good.
Yeah, so that's an interesting question. Definitely you have to have a degree in a STEM field. And even saying you have to have a degree, it depends on what you want to do, right? Like we have technicians that are working on Europa Clipper who are actually like turning the crank. And I don't think that they have degrees, might have associate's degrees or something like that. They won't let people like me actually touch the spacecraft, which is kind of sad because I would love to go in and touch it, but they're like, no, you cannot. So I think there's a bunch of different things. You definitely have to be in the STEM fields. A bachelor's for sure, a master's doesn't hurt. And then a PhD is not required. I don't have a PhD, but a lot of the people that I work with do. But what I'm finding in what I do on Clipper, which is like the ops, the operations, systems, engineering, a PhD wouldn't really help you. It's only if you want to go in and like really dig into some very specific technical part of it. And so if you want to be a scientist, you could get a degree in one of the sciences. I've got a really good friend that is a biologist and she works at JPL, but she is the scientist that's looking for biological markers and things like that. So you could have a lot of different paths. I will make another comment that I always knew that this is what I wanted to do. And so I got my degrees in it. I got my work experience in it. It was just kind of marching down the prescribed path. My husband is a second career engineer, and he didn't actually get an engineering degree until he was in his late 30s. And then he's been at JPL now for about 5 years. But he was a diplomat, and he was an Air Force program manager, and he stood up a biological lab at a university. Like he's done like all this other crazy stuff. And so his career path to getting to JPL looks very different than mine. And so it's, there's no one right way to do it, I guess is the short answer.
And I suppose you need a security clearance, right?
Nope. To do the planetary science missions like this, you don't need a clearance. I don't know I see the question in chat about being open to US citizens. Not necessarily US citizens, but you might have to be a US person, so you might have to have a green card. I think we do employ some foreign nationals, but I don't know exactly what their capacity is. So that would be something to talk to like HR about. But I would say being a US person, so at least having like a green card is probably what would be necessary to work with the spacecraft itself. You might be able to do like data stuff with science and not be a US person, for example. Okay, I see the next question. How can we get the public more excited about NASA and JPL unmanned missions? I feel like most of the wonder factor and buzz goes towards manned spaceflight. Is there a PR problem? That's an interesting question. So manned spaceflight is exciting, right? Like nobody's going to deny that. And so it's hard to compete with that. I don't know that I'd say it's a PR problem. I'd say that it's where we are in the missions right now. So we're about to launch. We're going to get a ton of press coverage if we launch in October. We'll probably get even more press coverage if we don't launch in October. So that would not be good. But hopefully we'll get a bunch of good coverage when we launch. But then it's going to be a quiet 5.5 years. And you're probably not going to hear about Europa Clipper again until we get there. And then once we start doing science, it'll be a big thing again, right? And then it'll be really exciting. And so I kind of feel like it's maybe just a product of where we are in time, right? Like right now we're doing a bunch of stuff on manned missions, and the unmanned missions are kind of in phases where people aren't just talking about them. But JPL, I know we've got a couple launches coming up pretty soon. So we've got Clipper, we've got NISAR, we've got SphereX, all coming up hopefully within the next year. And so I hope with those we'll start getting more press coverage because we're actually starting to do things like launching. You know what I mean? Do I work remotely? That is a very good question. As of last week, yes, I do. So I was in California, and then we decided to move back to Montana. And so now I get to do my job from Montana, which is pretty exciting. Join the National Space Society and you will learn of a group popularizing these missions and manned missions. Yeah, I think it's all about just being in the right networks, right? Like I get on LinkedIn periodically. I'm not a big poster, but I look at stuff, and there's a lot of people talking about different missions and stuff. So I don't know. I try to do things like this to get the word out and get people excited about it, go to conferences, talk to people. But I don't know. That's a tricky question. Ooh, what goes on during the 5-year transit? Okay, that's an interesting question. So people think 5 years until we get to the good stuff, right? But it turns out we have more than 100 unique things that we're doing, first time things, let alone like recurring things during those 5 years. And it's things like deployments of the solar arrays, deployments of certain instruments, calibrations, characterizations, turning things on and off, right? So we've got like 100 different things that we do for the first time, and then many of them we do every 30 days, every 60 days, every 6 months. So there's actually a lot of stuff going on. The other thing that's interesting, that's probably more interesting than that, is we do that Mars flyby and we do the Earth flyby. And so we have to do actually quite a bit of work to get into those and do what we need to and make sure that we can leverage the gravitational pull like we want to. And so there's quite a bit of activity happening, at least in the first couple years. Once we slingshot past Earth and we're like on our way out, we've got about 2.5 or 3 years left. That's when it'll get a lot more quiet. But we'll do practice runs. We'll exercise our procedures and our, practice doing flybys, practice like analyzing the data and stuff like that. But yeah, there's things to do that will keep us busy for those 5.5 years. Other questions?
Kendra?
Yes.
I was going to type this question in, but I figured it's just too much to type. I'm not a life member yet, unfortunately. I'm only I'm not there yet. I'm 62, but I've done a lot of work in IT. I have a bachelor's degree. I have a secure clearance. I've worked at Los Alamos. I've worked at the Pentagon. I've worked in flight simulation. I'm actually one of the few people that I know that actually have been trained to fly the space shuttle. We did an upgrade on it at Johnson years ago. And my industry was kind of decimated when everything went over offshore and stuff like that. So I'm kind of looking to reinvent myself. And I mean, I love what you're presenting. I don't have I have a bachelor's degree in technology, electronic engineering technology, but I've got a lot of experience in data analysis and things. Are there, and I live in Austin, Texas, right? So are there opportunities for someone like me with 30 years of experience in IT and project management and things at JPL? I mean, I love leading teams. I love being an individual contributor. I actually led my team in 1980, developed the world's first microprocessor controlled scuba diving computer.
Oh, wow.
I love technology. I love innovation. I love challenges. I'm not ready to retire yet, but I'm kind of tired of doing the next help desk IT project management thing. So that's my question to you.
So I will give you two answers. The first answer is yes, absolutely. I think that data analysis is a big challenge that we have at JPL, especially we're going to see with Clipper. We are going to get back so much data that it's going to be hard to get through it all and to do it smartly and with intention and being able to like analyze it in a way that makes sense. And so I absolutely think that we need data analysts and people who are really savvy on that kind of front. Unfortunately, on the other hand, we are having a hiring freeze right now. So they're not hiring anybody at JPL. And they're probably going to go do more layoffs, I would expect. We had a big round of layoffs earlier this year, and it looks like we'll probably have more layoffs later this year or sometime soon. So unfortunately, it's just not a good time to look for a job at JPL. But I would definitely keep your eye on it because I think we're going to bounce back, and I think that they're going to lift the hiring freeze, and we're going to need really good people that have good experience like yours. So I definitely would encourage you to keep looking and pursue that if you're interested.
Well, thank you very much. Yeah, and I did some work also at NASA at Marshall Space Flight Center. I was tasked to write some code that would allow for maintenance in between missions. So you know, I'm familiar with kind of the platform, you know, the background of NASA and things. Thank you for taking my question.
Yeah, no problem. Absolutely. I see another question. Have we landed any probes on Europa? We have not. This is the Pathfinder mission to get out there and see what's going on. And then we'll figure out if it is worth it and it makes sense to land either a lander, maybe a rover, or maybe just a probe. And one of the things that they've talked about is we see these cracks in the ice, and if we can get a probe to go down like through that crack and get into the water, then maybe we don't have to drill. Maybe we could just do that instead. And so that's one of the things we're going to look for is like, what are the opportunities for the next mission to get out there to do like real physical science data, science experiments. What else? You guys have great questions.
Well, if there's no more other questions, let's give Kendra a hand. So thank you for talking to us, and we appreciate it. So looking forward to hear from you maybe in a couple of years. Kind of give us an update. Right? Okay.
Will do. I would be happy to. Thanks again for the invitation. It was fun talking to you guys. And I put my email on there. I'm going to stick it in chat real quick too. At jpl.nasa.gov. And so feel free. Oh, no, I just did that to somebody directly. Hang on. Feel free to shoot me an email. I'm happy to answer any other questions that you think of later. I don't know. I do a lot of outreach to students. So if like your kid's school wants a presentation or something like that, I'm always happy to get that next generation of people excited about science and technology also. So definitely feel free to reach out.
Okay, great.
Great. Thank you very much.
Thank
Yeah,
you.
you're welcome. All right. Enjoy the rest of your night.
Yeah. All right.
Bye.
Good night, everybody.
Thank you. Goodbye. Good evening.